Okay, gonna start off with another one of Michael Greenacre's songs, just because they're all so good. Okay, gonna start off with another one of Michael Greenacre's songs.
One. Don't mean a thing if you don't do modeling. Do what, 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 do what. It don't mean a thing if you don't do modeling. Do what, 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 do what. It don't matter if you're frequentist or Bayesian. You just need a model with some alphas and betas and x's and y's and i's and j's and k's in, and it don't mean a thing if you don't do modeling. Do what, 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 do what. It don't mean a thing if you don't do modeling. Do what, 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 do what. Do what, do what, do what, do what, do what, do what.
I love that there's statistical songs. I can't believe that I didn't know these existed before. So thanks for that, Michael. All right, so we're live streaming now on YouTube. Everything seems to be working fine, and people on the Facebook page have the link, so that's good. I have some construction in my apartment right now, so I apologize if there's any like loud noises or something. I'm gonna stay on mute for everybody's talk so I don't disturb the speakers. It's 2:59 right now, so I guess I can start with basic introductions. I'm Russell Gray. This is the Ecology and R Web Conference Series Day 4. And today we're going to be going over some statistical concepts. The Ecology in R page is meant for the specific purpose of sharing code, networking with other like-minded colleagues, and well, I guess a lot of it is troubleshooting errors. So thankful for everybody that participates in that page, and this web conference series is a product of some of the members coming together and sharing their research and their expertise and everything. So I'm really thankful for the speakers that have participated so far and that are participating now and for the next two talks. So once the speakers are done talking, we can have some questions, and you can put those either in the chat box or the Q&A dialog box. I'm also monitoring the live stream on YouTube. So if anybody asks questions there, then I will also read them out for the speaker. So I can introduce our first speaker, who is Kyle Tomlinson from Zishuambana Tropical Botanical Gardens in China. And he's going to be talking to us about GLM and mixed models. I'll let him do the introductions. Kyle?
And I will try and keep track of time because the lecture is a little bit long. So let's swap to full screen. Okay, here we go. Okay. Oh, this is going to be something I didn't expect. Okay, so what are GLMs? A lot of us have already worked with normally distributed data, so I'm assuming that I don't need to say anything about normal data. But basically, generalized linear models, or GLMs, are what we use when the data is not normally distributed, but can be described by a known alternative mathematics distribution. So it can be described as a parametric model. And in much the same way as we would deal with normal data, because we can describe the data with math equations, we can also get means, and we can get variances. And because we can do that, we can do mean comparison tests and variance tests. So typical mean comparison tests that you should all be familiar with is the t-test. That's where you basically look at differences between coefficients, but those coefficients are actually being identified as mean estimates. And the other thing you do are variance tests, and the most common variance test we use is ANOVA, the analysis of variance. And these are trying to assess whether the model we fitted explains a significant amount of the variation in the response variable. So this lecture will be divided into a number of sections, which I hope are useful, and it will be quite simple because we only have 45 minutes for this. There is a little bit of code, and if you would like, I can share that code at the end with the data set, and you can run it yourself, but it is very simple. So the first thing you should be thinking about is what kind of distribution should I be using for my data? And what I want you to think about here is that we're talking about the response data. We're talking about the Y values, not the predictors. And what you should be thinking about with a GLM is maybe the following questions. Firstly, is my response data continuous or discrete? Secondly, is it hard bounded below? So what that means is that there is a minimum value beyond which we will not observe values, and we will encounter that value in the data that we collect. So if you think about count data, if you go out and count individuals of some topic, then you can imagine finding a site where you go and count and you find nothing. So you have a 0 count. And that is the minimum you can get, and it's also one that you might find. So that means that it is bound below by a fixed number. And then the third question is it bounded above? Is there a maximum value that I might expect in the data? And for this, you might think about proportion data. So proportion data lies between 0 and 1. There are many things that we measure that are proportional: rates, death rates, growth rates. And these are bounded below by 0, a minimum value, and 1, the maximum value. And we cannot find values outside that range. So this is a situation where the data is bounded on both sides. And that would be the third consideration. So continuous versus discrete, boundedness. And so I just want to go over a few distributions that would be useful under each of these considerations. And this would be the first choice you would make, the first decision you would make if you were going to use a GLM. So the distribution that we're all very familiar with is the normal distribution, and it has the properties that it is a continuous distribution and it is unbounded. So what that means technically is that, sorry, I'm going to go out of the slideshow because it's easier for me to use the cursor, is that the distribution is actually infinite. It goes from minus infinity to positive infinity, and it has a continuous stream of values. And we are very familiar with this if we look at plant growth rates, flow rates, masses, and even population sizes. So some population sizes that we use are very large numbers, right? If we think about human populations, in all places, we're most likely to get values that are larger than 0. Technically, 0 is the minimum value, but we will almost certainly never encounter it. And so it is reasonable to approximate large population numbers with the normal distribution. The next thing about it, which is not so important to learn today, is that the estimates for the mean and the variance are independent of one another. Most important thing for you to remember is that it's unbounded and it's continuous. The next type of distribution, which you may be familiar with, is the Poisson distribution. And the Poisson distribution is a discrete distribution, and it is bounded below. It is usually a minimum value of 0. And this is the kind of distribution that we typically use for count data where the counts are small. If the counts are large, we can use the normal distribution. The approximation is fine. But for small count data, we will use the Poisson distribution. And it has the property that the mean is equal to the variance. But for our interest here, the most important thing is that it is discrete and it is bounded below. The next type of distribution, which you may have encountered, is the binomial distribution. And the binomial distribution is discrete and bounded on both sides. So the binomial distribution is typically what we use for proportional data, data that lies between 0 and 1. It's also the kind of data we would use for binary data, where the only options we have are 0 and 1. For instance, if we were looking at survival data, an organism is either dead or alive. Dead equals 0, 1 is alive. Or maybe not, maybe you view it the other way around. Maybe dead is 1 and 0 is alive. It doesn't matter. The point is that it is strictly bounded on both sides. And it is a discrete distribution, and therefore the binomial is the most appropriate for this, or the simplest, most appropriate. I want to introduce two other distributions, which I guess most of you are not familiar with, and that is the gamma distribution and the beta distribution. But in light of what I've said about how you choose distributions for GLMs, these two are also important. The gamma distribution is continuous distribution, and it is bounded below at 0 again. So it is quite similar to a Poisson distribution, but the chief difference is that it will be used for continuous valued data and not for discrete data. Typically, the Poisson would be used for discrete data. And again, we can get estimates for the mean and variance, but they look a little bit different to the way we calculate them for the Poisson. And then the final distribution I would talk about here is the beta distribution. And as you can imagine, this is the continuous conjugate of the binomial distribution. So it is a distribution that is bounded below and bounded above. And the main difference from the binomial is that it is continuous rather than discrete distribution. And again, we can get estimates for mu and sigma squared. Sorry, mu being the mean estimate, population mean estimate, and sigma squared being the variance estimate. I assume you're all familiar with that terminology. Okay, so it can also be used for proportional data, but where the proportions are continuous. Okay, and then one more comment I'd like to make here is that please remember that when we use any distributions, we are approximating the natural process. We are not exactly representing the natural process, right? Most population values you measure don't explicitly follow the normal distribution. It's possible that they follow slightly more complex distributions, but the normal is the best approximation we can do, and it's close enough for us to make inferences. Same thing can be said about the other distributions. And it also means that maybe sometimes we don't need to go for very complicated distributions like the beta and the gamma, which can be difficult to work with. And we could use something simpler by just using the binomial and the Poisson distribution. And the inferences would probably be reasonably similar. Okay, so on to the structure of the GLM, and here we're going to talk about how you would actually write it in an R code. So what I want to introduce firstly, before we carry on, is transformation. This is an important idea when thinking about GLMs. So remember that when we're talking about regression, we are fitting linear models. A linear model means a straight line. Okay, so the best fit we can get through data is when the data between the predictor and the response is arranged in a way that it is linearly related.
Full screen.
Full screen, why? But if you do that, then I can't move my cursor. I need to do this, right? All right, what's the problem?
They're asking online.
They're asking online. Okay, sorry guys, if I do full screen, then I can't move things with my cursor, and I like to do that. My apologies. All right. Sorry. Okay. So as I said, so this is a linear fit. That's what we're trying to do, right? Because we're fitting linear models. So whenever we try to fit models, we try and make the relationships between the predictor and the response as linear as possible. So what I want you to look at below is a picture of a distribution. And if you look at that distribution, then you can see that it is actually a curved distribution. So X is got some values, but the Y values and the relationship between X and Y is curved. And the line, the straight line that we fitted through that data is not actually passing through the data very well. In the lower part of the distribution, it is underestimating the relationship. In the middle part of the distribution, it is overestimating the relationship. And in the top part of the distribution, it's again underestimating the relationship. And so that means the line is not fitting through the data very well. And that's because X and Y are not linearly related in the way they've been set up in this regression. So what could I do to fix this? I can use some kind of transformation that changes the shape of the relationship to make it straighter. And once I've done that, then I will fit the regression line afterwards. Okay, and so how would I do that? With normal data, you know that if the data is exponentially distributed, then you would use log transformation to make it linear. If the data was polynomially distributed, you would use some inverse polynomial distribution to straighten the data. Always, the point of the transformation is to try and make the relationship between the predictor and the response as linear as possible to get the best fitting line through the data. Okay, so, all right, now, having thought about that, let's think about what a GLM is. The GLM has got three parts. It's got the error structure, and that is the distribution that we are assuming that the response variable follows. So we just talked about that. Maybe the response variable is normally distributed if it's unbounded on either side. Maybe it's Poisson if it's bounded below. Maybe it's binomial if it's bounded on both sides. You need to decide based on the type of data you have. The next part is something which we call the link function. And the link function is a transformation that's used for the particular kind of distribution you're using to make the data relationship linear. And the last part is what we call the linear predictor. And this is just all the terms that you're using as predictors for the response variable. And again, the linear predictor looks like it does in an ordinary linear model. It is terms separated by plus or minus signs with coefficient estimates associated with each of the predictor variables. Okay, so speaking more about link functions, these are the transformations that we need to make the data as linear as possible. Well, then three that I will introduce here are the normal link function, the Poisson link, and the binomial link. And the normal link function is called the identity. And the identity is a mathematical term which simply means itself, right? If a data is normally distributed, we don't need to transform it. It is the best shape it can be for linear fitting. If data is Poisson distributed, it turns out that a good transformation is the log transformation. I'm not going to tell you why that is today, but that will be the transformation that would typically be used for Poisson data. And then for binomial data, there are actually a number of different transformations that we could use to make the binomial values linear with the predictors, but the most common one that is used is the logit transformation, right? So these are the transformations that we're using to set up linear relationships between the predictors and the response data. And they are being applied to the response data, right? They're not being used on the linear predictor, which is all the predictors. It's just being used on the response data. So just to say that again, link function is a transformation that changes the response to an unbounded linearized form suitable for regression. It does not necessarily make the response normal. It ensures that the estimated values are subject to the bounds of the original distribution of the response. So this transformation, when we go back to the original data, that the predicted values will be in the same range as possible in the original raw data. Okay. About the linear predictor, well, the linear predictor is just the predictor values in a linear relationship, and they are set up in much the same way as you would for an ordinary linear model with a normal response. You can have main effects, you can have interactions, and you can have polynomial terms. As a note, I would just like to point out, because we're trying to set up linearity between the predictors and the responses, I always check the distributions of my predictors as well. If they are exponentially distributed, then I'm sure that the line you are fitting is very bad, right? So it is my advice that you also look at the distribution of your predictors and see if they are very skewed. If they are very skewed, you should try and make them more normal before you set up the linear relationship. Okay, a GLM example. Okay, so this is the problem. At what age do fledgling birds start to fly in a certain population? So the response data is birds flying or not. So not flying is 0, flying is 1. This means the data only has two values, 0 and 1. It also means the values are bound below and above, 0 and 1. So the correct distribution to use here would be some variation on a binomial distribution, right? Some distribution which has that property that the values are bounded on both ends. And we have a predictor value, and the predictor value is predictor variable, and that is age in days since the fledgling emerged from the egg, right? And if we were to plot the data that's been recorded from many different nests of many different fledglings, this is what we can see. If the fledglings are very young, then basically they can't fly. Right? So most of the values for very young birds are zeros. But at some point, about an age of maybe 10.8, I don't know, 10.8 days, the first bird is able to fly. And as the age increases, the number of birds that fly also increases. And eventually you can see beyond about the age of 14, all birds beyond the age of 14 can fly. Right? So there's been a switch in the behavior from zeros, no fly, to ones, fly. And so a good way to represent this relationship is a sigmoid function. And the sigmoid function is a line which switches between a minimum value and a maximum value. And it is bound by that minimum value. It actually asymptotes to it. It will never reach it exactly. And it is bound at the top as well. And it asymptotes to the top value and will never reach it either. So it is a continuous distribution, but it has this good property that is bound between 0 and 1. And what it does for us, which is very nice, is that it gives us the switch, right? So there's been a switch in the behavior from zeros to ones somewhere in the point where this line is flipping between the lower line and the upper line. And what I want you to think about is if you look at all of these dots here, these represent very many different birds that were sampled. And if you were to take those birds and count how many of different ages there were, you could work out the proportion that were flying at any time based on the age. So at very young ages, maybe you measured 5 birds and they were all zeros, right? So the proportion that were flying at age 8, I guess, or 9 here, they were 0, right? All were zeros. At an age of about 11, maybe 1 out of 10 of the birds you measured is able to fly. At an age of 13, about half of the birds you measure are able to fly. And similarly, as we increase, you can see that the proportion of birds that can fly, that are successful in flying, is switching to higher and higher values, right? And so that's exactly what we would like to fit with our data. We want to show the switch in the behavior, that the proportion of successes, which is the number of ones, is increasing with age. Okay, so this particular line that we fitted, which is called the sigmoidal line, is best fitted by using this logit transformation. So I told you the logit was a transformation that sets up linearity between the response data and the predictor. So between the y values, which is flying or not flying, and the x values, which is age of the fledglings, right? If you do this, the P here represents the proportion of successes, the proportion that are able to fly. So at small values, P is very small. At large age values, P is very large. And that's exactly what the model will fit if we do this transformation. This transformation will give us the sigmoidal shape. And importantly, once we've made the regression, we can then back transform and make this prediction line. Sorry. So I guess I'm missing a step here, which you can't see. But essentially what happens is once I have all of these dots, all of these proportions of successes at different ages, these I will transform with the logit transform, right? And then I will fit this data, these proportions, against the age. And then after that, I can back transform to the original range of my data to get this sigmoidal shape. So the regression line is not being fitted directly as a sigmoid. The regression line is being fitted as a straight line on a transformation of these data. This line you're seeing, this red line, is the back transformed values. It is the prediction line made after I have undone the transformation. I hope you guys are all keeping up with me. All right. So the message I want you to take home here is that the transformation allows us to fit the data in a linearized form and then back transform to give us data in the original range that satisfies the property, the data properties of the original range. Okay, and the data property here is that the predictions must lie between 0 and 1. And what we would like to see is that the direction of this line actually is consistent with our data, which it is. What we can see is that with age, the prediction is that the ability to fly increases. Okay, the next part is making inference with GLM, and here we will actually introduce some code. And I think this is the question that most people in the course were asking about. And so I hope to give you some answers here, but if not, you can always ask me more questions afterwards. Okay, so first thing, the GLM function itself. I assume that most of you are familiar with this in R. If you are familiar with the LM function, the LM function is what we fit for linear models, and it's written LM, and inside the brackets, we would have the response variable and a tilde, and then the predictor variables. In this case, I have a very simple model. It is the number of aphids in response to some treatment. And it comes from a data frame, which is called aphid2. And because it is the number of aphids, I'm talking about count data, right? And if I'm talking about count data, then the family I need to use is Poisson. So whenever you set up a GLM, you need to provide the equation, the predictor, and the response and the predictors, the data frame where the data comes from, and you need to specify the family so that the GLM knows what assumptions it should be making, and what transformation it should use, right? If you set it up this way, it's going to say, okay, it's Poisson data. I must use the log transformation on this data before I do the regression. And if I run this data, then this is the output, this model, this is the output that I will get. And what it gives me is something called deviance residuals. Then it gives me coefficients. I'm assuming that you're all familiar with the linear model. So you would have seen a coefficient table. And a coefficient table always gives us the names of the predictors, starting with the intercept, and then each of our predictors, whether they're continuous or categorical. It gives us estimates for the relationship between the predictors and the response, standard errors, and then the difference from the normal table is that it gives us something called a Z value and probabilities based on the Z value. Previously, in the normal distribution, this would be T values and probabilities based on the T distributions. And then the last piece of information I want you to notice are these three lines at the bottom here. One says the null deviance, something called the residual deviance, and the AIC. And I, again, am assuming that you're all familiar with the AIC. We will not talk about it in depth here, but if you don't know, you can also ask me afterwards, and I can explain it in more detail. Okay, so we've set up a basic model, and the next question is, how do we decide whether things are significant or not in the model, whether we really have an effect or not? And so when we do this, you need to remember that because we're doing generalized linear models, the data is not necessarily normal, and that means that the residuals are not normal. And as a result, we cannot use t-tests or ANOVA because both of those methods assume that the residuals are normally distributed. But that is the one assumption that we throw away when we use GLMs. So we need to make evaluations of significance in a different way. And what we do instead is we can still do mean comparisons. So mean comparisons is when you look at the coefficients and you evaluate whether the coefficients are significant. And in a normally distributed data, you would use a t-test, but now we use the Walt Z statistic, which I just showed to you in the output. And if we want to do variance analysis to ask whether our model explains a significant amount of the variation in the response variable, we can't use ANOVA, but we can use deviance tests, and we can use AIC comparisons. And I will introduce both the Z statistic and the deviance test. But the Z statistic I will talk about very briefly. The Z distribution is a kind of normally shaped distribution, but it is a single distribution. And this means that it doesn't depend on degrees of freedom. So there is only one, there are not multiple. When dealing with normal data, we have this problem that the T distribution changes its shape based on the degrees of freedom for the residual error. We do not consider that here when using Z tests. And the Z distribution is used because it has been shown that if you take the ratio of a mean estimate and divide it by its standard error, that distribution, those ratio data follow the Z distribution approximately well, so we can use it. And so we have a way to directly evaluate whether our coefficient estimates are significant or not by setting up these ratios. So if you go 3.51 divided by 0.03, I can tell you that it will give you a Z value number similar to this number here, all right? And that number can then be compared against the distribution from the Z normal distribution, and we can conclude in this case that Z is very large, so it seems to be significant. Same thing for the effect we're actually interested in, which is the treatment L, and it also generates a large Z value, and that's significant. So we could draw inference this way. We could look at the Z values and Z probabilities directly and conclude, yes, there is support that this predictor is explaining the response variable. So the other method we can use is deviance. And deviance is basically the GLM equivalent of ANOVA. It's how we look at variance and ask whether our model explains a significant amount of variation in the response variable. And because we have limited time, I cannot explain this to you in too much detail, but I do need to introduce the concept of maximum likelihood estimation, right? I hope that you have all seen the word likelihood, because most GLMs and higher order models are based on likelihood estimation. They're not based on least squares estimation. As far as I know, that only works for normal data. It cannot be used for other types of distributions. So we use something called maximum likelihood estimation. And I can't explain this to you in much detail, but what I can tell you is that it sets a likelihood is a function that uses the data you collected and an assumption about the distribution of that data, whether it's binomial or Poisson or normal, to make a very complex function, which we call a product function. And this product function is represented by pi. You're used to seeing sums, but if you see pi, that means these are functions that are multiplied together, right? And what this means is it's saying this value here, it makes a function of all of the data you have combined with the distribution you're assuming. And that function actually has values, right? Because you've given it real data. And because it is a function, it has a shape. And because it has a shape, it also has a maximum value, right? And the important property here is that what we assume, and I guess has been shown to be correct mathematically, is that the most likely value for our estimates, so our coefficients of our predictors, the most likely value is at this turning point, right? So the highest value on the likelihood function, that's the point where we get the best estimates for our coefficients. Okay? Right. So that's very important. And we call this maximum likelihood estimation. We make a likelihood function and we find the maximum of that likelihood. So what's happening with deviance? Well, deviance is doing something a little bit more complicated. So what it's doing is, let me talk about three models here. There is a model called the null model, the model called the fitted model, and the model called the saturated model. And what I want you to notice about these models is that they have different numbers of predictors, right? So the null model has no predictors. It only has an estimate 1, which means that it's only generating an intercept, right? The model fitted is our model. It's the model that we have submitted for analysis, where we have two predictors, x1 and x2, and we're asking whether they can explain y significantly. And then the saturated model is the complete opposite end to the null model. It's the model where we have as many predictors as we have data, right? So technically, this model can explain all of the variation in our data, because if you have as many predictors as you have points, then you can draw a line through every single point in your data. So this is the maximum fit that we can get to the data, right? It also means that if we were to generate a likelihood from this model, this would be the absolute maximum likelihood we could get with our data and a model, right? It would be a model for which we have one predictor for every data point we collected. And the minimum likelihood we can get is for the model where we have no predictors, and that is the null model. And our model, the model that we fit, is lying somewhere in between these two extremes. And if you think about what ANOVA is comparing variance explained by different parts, right? And you can almost think about it as a proportion of variance explained by your predictors. And if you look at this geometrically, you can see a similar thing here. You can see that the total variation in this data is the difference between the saturated model and the null model. And the amount of variation that our model explains is basically this much of that total variation. Can you see that? Basically, there's a likelihood, maximum likelihood estimate for each of these models. And so what we actually do when we talk about deviance is the difference between likelihoods. So if we talk about the deviance of the fitted model, we're talking about the difference between the likelihood of our model and the saturated model. And if we talk about the deviance of the null model, we're talking about the difference between the likelihood of the null model and the likelihood of the saturated model. And if we want to ask the question, if our model explains a significant amount of variation, then we want to compare the amount of variation explained by our model relative to the total amount of variation in the data. And that is what we call a likelihood ratio test, where we look at the deviance of the residual deviance, the big amount, divided, the residual deviance is our deviance, this difference divided by the null deviance, which is the larger number, okay? And it turns out that these ratios of deviances can also be described by distribution. They're described by chi-squared distributions, and the chi-squared that we need depends on the difference in the number of parameters between the inner and the outer model. And I won't get into an explanation of that now. Okay, so when we do this analysis, this is, if you go back to the summary statement from our model, right at the bottom, it actually gave you estimates for the deviances. It gave you the null deviance and the residual deviance. And so you can see the null deviance is always a larger number than the residual deviance. The next thing to note is that the degrees of freedom for the null deviance is 59. And that's because this is a model with only one parameter, and that is the intercept, right? And the residual deviance, which is our model, our fitted model, this is a model with two parameters, the intercept and the estimate for the treatment. And so the difference between these two models is only this guy here. And so the difference in the degrees of freedom between these models is only 1 degree of freedom. So when we do a chi-squared test and a likelihood ratio test, it's going to compare it against a chi-square with 1 degree of freedom, because that is the difference in the number of parameters between our models. These deviance likelihood ratio tests are always comparing nested models and asking whether there's a significant change in the deviance, which is the GLM equivalent of variance explained by the model. And so this is very easy to set up in R. We first write out the full model that we're interested in, which is just n aphids as a function of treatment. And we set up the null model, which is n aphids as a function of 1. Whenever you write the null model, you always have to say y tilde 1. And then it knows it needs to fit a model just with an intercept. And if we run these two models, we can save the output into names. So I'm calling this GLM result mod 1. I'm calling this null GLM result mod 0. And to perform the likelihood ratio test, I just need to use the command ANOVA, open brackets, mod 1, comma, mod 0, and specify test equals chi-square. There are other tests we can use, but the most typical one we use is the chi-square. If I run this command, it's going to take the result from model 1 and the result from model 0 and give me a ratio. And it says here it's giving me an analysis of deviance table as opposed to an analysis of variance table. And what it shows you is the residuals for each of the models. And so our fitted model has got 58 residuals, which means the total data set was 60, right? There were 60 data points, and we lost 1 degree of freedom for each of the estimates we made, the intercept and the treatment. And the null model only loses one value for the intercept. And so the difference between these two models in terms of the residual degrees of freedom is only 1, right? And when we take the ratio, it shows us that there's been a huge change in the variation explained by the fitted model versus the null model. And that difference is actually recorded here. This minus 766 is just the difference between these two numbers, right? And it compares this against a chi-square distribution and concludes that it is a highly significant change. So our model that we fitted to the data is explaining a huge amount of the response variable. Okay, so one or two of you asked about model selection. I don't have time to talk about that because that's basically a whole lecture. But if you are familiar with model selection procedures, then I can tell you that you can use pretty much the same as you would use for normal data. You can use subset selection, but here you would use likelihood ratio tests or AIC comparisons or Z tests to choose models, or you can use model averaging. And as far as I am aware, you can just set up model averaging in the same way as you would for linear model in the Moomin package, and with the assumption of comparisons made on the AICC as a criterion. And this is typically used simply because most of our data sets are small, and this correction on the AIC is better for small finite data sets. Okay, the last thing we're going to talk about, I think it's the last thing, is model checking in GLM. And just to remind you that in linear models, we always have to check whether the data is, oh, sorry, let me change that quickly, the errors or the residuals are normal and homogeneous. And in GLM models, we should also check homogeneity, but we need to check for something called overdispersion. And what overdispersion is it's when, it's when the variance estimates are larger than the mean estimates, right? So the variation in the data generates variance estimates that are bigger than the estimates of mu. And when this happens, for reasons that I don't understand, it leads to a problem of underestimated standard errors. This is the main outcome of overdispersion. And because we get underestimated standard errors, we are increasing the probability of type 1 error. And if any of you are familiar with this, type 1 error is the chance of finding a significant effect when there isn't one, right? We make the test much more sensitive. One way we can see the overdispersion problem is if we fit the homogeneity plot, but the standardized homogeneity plot. So if you're familiar with the residual plots that you get from a normal model, you always have 4 plots. And the bottom left corner is the standardized residuals that have been made strictly positive, right? And what we expect is that the average residual size that we would want in a good model should be 1 or less, right? So the average size of the residuals in our model here can be seen by the red line. This red line is basically fitting averages at any point in the data. Now, don't be stressed out by the shape of this plot. Remember that this data is treatment data, so it has fixed values for treatments. And that's why we get these two strong columns of residuals, it's because of the two treatments. But you shouldn't worry about that. The important thing to notice here is the size of the average residual. And what you can see is that this fitted line is showing you that the average size of the residual is 1.5 for the one treatment, right? So it is much larger than 1. So this is one way that we could diagnose that there is a problem with overdispersion. But another way we can do it is we can actually use a ratio test called the deviance divided by the degrees of freedom. And this is actually asking, if we look at the average size of our residuals, are they greater than 1? It's more of a formalized test about this. And the way we do this is we set up a chi-squared sum, which is our deviance. And basically, we take all of the residuals from our model. We specify that we want Pearson residuals, and we sum the values of those residuals. And then we simply divide the sum of squared residuals by the degrees of freedom of residuals. So the degrees of freedom associated with the error in the model. And if this ratio is much larger than 1, then we can conclude that we have an overdispersion problem, right? So basically, this ratio is the important thing. In this case, you can see in our data, the ratio is 5.8. So it is much larger than 1. And we would diagnose that we have overdispersion. If the ratio is much less than 1, then we have something which is called underdispersion. But I've never found any evidence to suggest that underdispersion is something we should worry about. So typically, we tend to ignore it. If any of you know differently, that underdispersion is an issue, I'd be very interested to hear about it and learn more. But I've only ever heard worry about overdispersion. Okay, so that's easily done in R. Basically, you can see we made our model. So this is the result of running the GLM. And we just plug that result into this sum to make our chi-squared sum. And then we can also get the degrees of freedom for the residuals from our model and easily calculate this ratio. So that's how we would diagnose that we have an overdispersion problem. Something else I just want to point out here is that in the case of binary data, it's not so simple. Binary data is data where we have zeros and ones. And in this situation, it's not very clear how to deal with overdispersion. And I can tell you that I don't understand this very well. That's the short answer. But the advice that I've always been given is that you need to use something called a binned plot. And a bin plot basically bins the residuals for different sizes of fitted values and asks whether the variation in those residuals is more than we would expect by chance across within that same bin. And the plot gives you these kind of gray confidence interval lines. And what you need to check basically is whether the dots lie inside or outside the gray line. And if most of your dots are lying inside the gray line, then it is thought that probably you do not have a problem with overdispersion. If most of your points are outside of the gray lines, then you need to go back and look at your model again and think about whether you need to handle it differently. Sorry, I know that's not a very satisfactory answer, but it's one of the areas where I don't know the answers properly yet. Okay. So if we diagnose that we have an overdispersion problem, what should we do? So there are a number of ways of dealing with overdispersion. I am not going to show code for how to do that here. I'm just going to tell you what you could try. So the first thing you could do, which I teach in the stats course we do here, is you could use a quasi-distribution. And this is like taking a pickaxe to your analysis and cutting it so it fits the data better. So my short advice is, although I teach it, I strongly advise against using it. It will give you an analysis that is more conservative, but it is done in a very physical way, and it does not rely on a proper distribution. Essentially, what it does is it diagnoses the problem, how much the residuals are too large, and then it divides those residuals to make them smaller, right? So it very much is a pickaxe method for solving the problem. What you should rather do is think more about your data and think if you can use another distribution that has a proper likelihood. And within this group, you might think about two types of problems, which is that maybe you really have a proper variance inflation problem, in which case you might want to use the negative binomial model, or you could use a generalized linear mixed model with something we call an observation level random effect. And what that does essentially is fits a normal distribution as another part of the variation. And so what you're setting up is a compound description of the data, which has both a binomial process and a normal process inside it. Binomial or a Poisson process and a normal process. So these fixes are generally more complex distributions. That's the reality. And the point being that the Poisson and the binomial are very simple representations of data. And we have a whole range of models which are more complex that can describe more complicated data. And then the next set are what I've termed here the mixed process distributions. And among these are zero inflation models and hurdle models. And just to think about a zero inflation model, a good example is if you are recording birds at wetlands and you want to know how many birds there are at the wetland. Some days when you go to the wetlands, there are many birds and you can get counts of birds. Some days you go to the wetland and it's dry and there's no birds, right? And what's going on there is two processes. There is the abundance of birds, and that can be described by the Poisson, and that's related maybe to how much food there is in the wetland when it's there. And there is a second process, which is the binary process. The wetland is wet or it's dry, right? And that is a separate process that you need to describe. So these mixed process models will allow you to describe both parts, both the presence and absence of water and also the abundance of resources, okay? So usually more complex models are required to solve these overdispersion problems. Okay, and then the last thing I'm going to say here is that when thinking about a GLM, you want to think about linear models in general and the assumptions we make here. And these things you should keep in mind. First, that the model you've set up is reasonable. Secondly, the terms have to be additive, otherwise it's not a linear model. Third, try and get linearity between the predictors and the response. Fourth is independence of errors, which we will talk about a little bit in the next lecture. Fifth is homoscedasticity. This is that the range of residuals should be approximately the same size for small fitted values and for large fitted values. And finally, because they're GLMs, we don't need to worry about normality of errors. But if it was normal data, we would have to worry about the last one. Okay, and that is the end of this lecture. Are there any questions? Maybe Russell, you should take over again.
Yeah, so we have quite a few questions and comments for you. The first one by Anastasia, she asks, what do we do for model selection if we have a bigger data set, since the AIC is more preferred for smaller data sets, as you said?
Well, I don't think I have a strong opinion about this. I'm not actually sure what the properties are, but I assume that the AICC will converge towards the AIC for large data sets, but I don't actually have a strict answer about that, Russell. I'm not sure. When she says large data set, how much data is she talking about? That would be the question, right? So for each parameter, ideally, you should have at least 20 data points. then you'll get good fitting. So if she has at least 20 data points per parameter she's estimating, so that means if she had 5 parameters that she was estimating, then she would need 100 data points. If she has that, then probably AIC is fine, right? It likely won't yield very different differences. But my guess, without knowing for sure, is that the AICC basically converges on the AIC for large data sets. And so you can just keep using the AICC.
Okay. And Edberto asks, I have a data set based on difference of growth between 2 periods, T final and T initial, and over time, some regions experience loss. I was trying to apply GLM models to explain the influence of some variables of those differences. However, because of the nature of my data, negative and positive values, I could not find a proper family distribution. In this case, what is your suggestion for it? Should I consider transforming my data?
So it's going up and it's going down. I mean, it's just... So the question would be, so the trick is the negative values. He doesn't know what to do with the negative values. Wow. Gosh. I mean, the one way that I could think of to hack that is, it depends how negative they're going. If they're just dropping a little bit, then he can just use a fixed coefficient shift, right? So that would just be, so growth data is typically exponentially distributed, right? So if his data looks normal already, then he can just use the normal distribution. But if it is exponentially distributed, then I guess the simplest would be to, I'm just going to make an extra slide here. He could try something like this, right? So where A is larger than his most negative number. Understand? So basically, in doing that, the problem with exponential data is that you can't get the log of negative numbers. But if you choose a value that is larger than the smallest negative number you have, then it shifts all of the values into the positive range, and then log transformation is not a problem. So that would be one possibility. Another possibility is maybe he could consider a hurdle model. I am not sure that this is the best solution, but that would recognize 2 processes. One process is positive or negative growth. So process 1. And process, damn this thing. All right, sorry. Process 2 would be positive growth. And so for this case, he would have to code the values as zeros for negative numbers, right? Let's just do this here. And for the second process, for the values where the individuals grew, then he could still just keep positive growth. So he would only use a hurdle model if he had good reasons to think that the process driving positive versus negative growth was something different to the process driving positive growth, because essentially we're assuming 2 different distribution, different processes happening to his data. But if it's just to make values, make everything positive, then I guess log plus a positive shift would be the best. And that's what I've used in the past when I've had that problem. I've just shifted it to the positive range. And that means I don't lose any of the data, right?
Okay, we have one question in the YouTube feed. They said, you mentioned assuming distributions for the data while the assumption for distribution is really for the residuals. As such, wouldn't the distribution of covariates be irrelevant given that the residual diagnostics really relate, at least to normal distributions, to the difference between the linear predictor and the data?
He's asking about transformations to the predictors, I guess. So my point there is the residual plots are clearly just about the response data, but the fit of the line will not be. Well, you will fit a line, but whether it will be strictly linear if the predictors are log exponential. Yeah, I guess I should have drawn that. But basically, the fit of that data will run through the data, and I'm not sure that you'll be able to diagnose the problem in the residuals. So this is more about thinking about how to fit your data to get the best linear distribution, right? Whether you would be able to detect, you wouldn't be obviously able to detect a problem in the distribution of the predictors from the residual plots. Yes, the residual plots are purely describing the distribution of the response data. So that's not the way, not the place to look for this problem, right? Rather, plot your data, plot out the predictor versus the response, and look at that distribution first before you make decisions.
Okay, and we have another one that says, regarding the assumptions of independence of mean and variance of a normal distribution, independence is a concept reserved for random variables. So could you elaborate what you mean with this?
My gosh, I think he's talking far too over my abilities to answer that question.
Okay, I can move on to the next.
Yeah, that's obviously somebody who's a statistician and should answer the question himself.
They said the MLE of the variance actually depends on the sample mean. So it seems impossible to assume the mean and variance estimators are independent. As a comment in your slides, you wrote ETA equals log of y. Given that the data is transformed in a GLM, do you mean the linear predictor is equal to the G of the conditional expected value?
Okay, this is obviously a mathematician or a statistician. Sorry, which slide?
Let me ask.
This, I guess he's talking about. Say the question again.
So he says in your slides you wrote log ETA equals log of y somewhere.
Yeah. So okay. Okay, so maybe that's not a good way to put it. Maybe just the link function, of course, is actually this thing here, right? It's the actual function that's doing. Okay, so maybe it's wrong to call it that. Sorry. Let's just change this name to. Okay, all right. Okay, so basically, this is a relation that's set up for doing the fitting. Okay, sorry, good point.
Okay, we have one in the comments here. Pietro says, suppose you perform different models using different distributions like Poisson or negative binomial, but with the same structure in terms of covariates. Is it correct to use AIC to assess what is the best model in relation to the distribution?
That's a good question. So basically saying, if I use different model types, can I assume the AIC will generate the same possible values? Shit, I don't think I can answer that very well. I can come back with an answer afterwards. I have done that, and off my head, I cannot remember whether it was valid or not, but in my memory, I have published papers where the models were fitted and compared using AIC, and they were variations on the same binomial model. But yeah, I don't know the answer, I'm sorry. I'm not a statistician, so I don't know the answer. Mm-hmm.
Okay.
You're finding all of my limitations, yeah?
Well, I mean, it's good to clarify more points too. Yeah. We have another question. How do I deal with heteroscedasticity?
Well, so sometimes you can't, right? So my main consideration is in GLMs is I try and establish that the average size of the residuals is less than 1, right, using the deviance. And then I assume that the fit of the line is sufficiently good that I can trust the fit of the data, right? Because if the residuals are all less than 1 on average, then actually the line is fitting reasonably through the data, right? So it's possible that maybe the residuals are smaller at one end than the other. But if the average size of the residuals is less than 1, do I need to worry about it? I don't. I just assume that it's acceptable. Basically, the residuals are on average smaller than 1. I trust that my data is reasonably fitting the data. Certainly in binomial models, especially in data where you have zero inflation, it's very hard to get a non-heteroscedastic residual plot. But check the size of the residuals. If they're small, it's okay.
Okay, that looks like it's it for the questions right now. If you want to go on to your next part.
Okay, I'm just writing down variance comparisons, AIC comparisons between models, and then I can look that up and try and give an answer later.
Yeah, and I'll also be posting this in the ecology in our group. So if anybody wants to further discuss or try to ask questions, you can ask there, or I assume you may give your contact information for people to contact you after.
Yeah. Okay. All right. Yeah, sorry guys, there's some limits to my knowledge for sure. I'm an ecologist, not a statistician. Okay. All right. So let's kill this one. Sorry, save that. Sorry, I just got to find, where did I put it there? Okay. Okay, so Mixed models. So this will be quite a brief introduction again, because 45 minutes. And I'm assuming low level of knowledge here, but there's clearly some people in this group who have very high level of knowledge. So back to the assumptions about linear models and what we worry about a lot in mixed models, which is, again, the main assumptions are that the model should be meaningful, terms should be additive, we try and set up linearity between predictors and responses, and in mixed models, we worry about something called the independence of errors. We do need to make sure we get homoscedasticity, and for normality, it will depend on whether we're dealing with a normal response or a non-normal response. Obviously, if it's a non-normal response, then we don't need to worry about normality of residual errors either. So just some examples to explain when we might encounter these kinds of problems. And the first is, I just want to talk about what I call spatial blocks. So if you look at this picture, what you can see is a catena. And along the catena, we have some trees growing. And the question of interest, not a very important one, but just illustrative, is the research is interested in the difference in height between tree species. And what you can see here is that the heights of the trees changes based on where the trees are growing in the landscape. So at the bottom of the hill, the trees are really big, and at the top of the hill, the trees are really small. And so in all places, if you look inside each location, you can see that the differences are always in the direction that the pine tree is taller than the broadleaf tree, right? But if you were to use all this data and ignore the underlying gradient, then you might conclude that there's no differences, because the variation between the sites is much larger than the variation within the sites, right? And so there's some other environmental variable in the background that is causing variation. And we're not interested in that, that background information. We only would like to account for it because it's making our tests weaker if we have it there. And so one thing we might be able to do, if we have no information about what this background variable is we could maybe block the data, and we could combine individuals that we measure that are close together into groups, right? So in this case, I basically grouped individuals on the top of the hill, grouped individuals in the middle of the slope, and grouped individuals at the bottom. And in doing this, I am able now to treat this grouping thing as another predictor in my model. And this grouping thing is able to extract information, the variation between these locations, right? And it will identify this as variation in the data and take it out of the model. And in doing that, it will make my tests more sensitive for what I'm really interested in, which is the differences in the heights between the species. And what we call this process, we could call these blocks. Maybe you could call them groups if you want to, but blocking is a very common name for this. And it's where we try and get all of our treatment types inside closely confined spatial areas, and we treat them as part of the same group. And we have all of the treatments or some of the treatments in other areas, and we identify those groups as well. And we call each of these locations a block. And with these blocks, we can actually add this parameter into the model. And we say we have block 1, block 2, and block 3. And these are levels. It becomes a factor. And we can then estimate coefficients that explain the variation created by these blocks. And so this is called blocking. And what I want you just to remember here is the purpose is to remove variation from the landscape that's changing the response that we're interested in. But that variation we're not interested in. We don't really know how to classify it, right? We just want to account for it. And blocking is a good way of taking care of extraneous variation in the data, because there's many, many things in the environment that could be causing this variation. Okay. All right, so another situation where we might consider this problem with mixed models is things we call subject effects. And so I want you to think about some kind of problem where we're looking at the blood sugar of dogs, and we're interested in how that blood sugar responds to some treatment versus a placebo. And we're interested in how that changes over time for some reason. And what I want you to notice is that each dog, each line represents a dog, right? And these are its blood sugar levels over time. So the response variable is blood sugar, right? There are two predictor variables here. There is time and there is the treatment. But there's something else going on here, and that you can see from the slide, which is that each of the dogs has a set of values. And you can see that each of these dogs has a range of values, right, that are associated with that dog. And so any measurements that we take on that dog are basically going to be stuck inside that range. So they are connected to one another. They are related to one another, right? So they have what we call dependence, right? And we need to recognize that dependence, because if we don't, then the residuals from the model, if we ignored these values being tied together in individual dogs, then we would have dependence in our residuals. And what we're trying to establish as much as possible is independence in our residuals, because one of the properties that we require for the residuals of our model is that they are independently distributed. And a lot of what mixed models is about is trying to establish as much independence as possible, in addition to also accounting for variation sources. Okay, so I hope it's clear to you that there are differences in values here that are nothing to do with the treatments are in blue, and nothing to do with time, but are strictly to do with which dog the measurements were taken on. So these are subject effects. We have to take account of the fact that each of the dogs has its own possible values, right? Now, we don't care about the differences in individual dogs, but we need to use the dogs as our experimental units. So we treat these dogs as some kind of random effect, something that we need to account for in our model to take care of the variation that they explain. All right, so fixed effects, fixed effect. All right, so somebody online asked, what is a fixed effect and what is a random effect? So a fixed effect is a predictor that we care about. It is in this case, it's a drug treatment, and it's also time. We care about how the blood sugar is changing over time. A random effect is a predictor we don't care about, but which might be causing variation in the data that we can account for. And in this case, it's each of the dogs, because we're taking measurements repeatedly inside the same dog. Okay, so just to remind you again, so fixed effects are things that are in our hypotheses, things that we want to know their effect on the response. Random effects are other things that are causing variation in our response that we want to take care of. Okay, so structure of a mixed model. A mixed model has this kind of form. This is a very, very much reduced form, and I can't spend much time on this again because we're in here 45 minutes. But basically, the structure of a linear model, which has got fixed and random effects inside it, would look like this. It has a response variable, which is y. It has a fixed part, which you should all be familiar with. This is the x's with their coefficients. And then it has a part which is called the random effects part. And it is the individual levels for the random effects, and they also generate coefficients. And we will see that just now on a slide. And then there's the information that we cannot explain with both our fixed and random effects, and those are called the residual errors. And related to this, we get two things. We get two variances. A variance, which is related to the distribution of the residual errors, and a variance, which is related to the distribution of the coefficients of a random effect. And because we have these, one of the important things we're trying to do with a mixed effects model is we're trying to extract this information out of the model, because this is variation in our data, right? It's causing our tests to be weaker. And so by including this, we can extract this additional variation. In expanded form, this is pretty much what a mixed model regression looks like. You have a vector of the y responses. You have vectors for each of the x's. And you have a vector for each level of the random effects. And they have their own coefficients in much the same way that the predictors, the fixed effects predictors have coefficients. And then there's the information that we cannot explain with each data point, and that's the residual errors. And these coefficients, they are typically normally distributed in linear mixed models. And the errors, we also require that they are normally distributed, right? Because right now we're dealing with linear mixed models, so we're assuming that the residuals of the model will be normal so that we can use normal tests. Okay, so just to go over that previous problem again, just maybe to try and visualize this a bit more. So remember that the response was blood sugar, and now I'm only going to consider the one fixed effect, which is time, and this is how blood sugar is changing over time. And the random effect is dog ID, right? Each dog needs to be identified because it's got its own values. And you can see the values measured in each dog in these different colors. When we fit the model, we're going to end up with something like this. We're going to have sugar as a function of time. So we will have one coefficient representing the overall slope relationship between blood sugar and time, which is just a straight line. And because we are only fitting random intercepts, we are actually making a single intercept for each of the dogs, right? And so what the B's are, they're actually the differences between the fixed effect estimate of the intercept and the locations of each of the dogs on that intercept, right? So that's what the betas actually are here. And these betas are distributed in a normal way around the mean estimate. Clear? Okay, and then I've added just at the top here that, of course, these are straight lines we're fitting, and they don't explain all of the information. There's still some unexplained information, and that's all of these differences between our fitted lines and the dots, and that is the residual error, all right? Of course, the red dots are right through all of the data. I've just shown it on the top line because it's easier to see it that way. So that's basically what's being fitted in a very simple mixed model. Okay, so there are numerous packages in R for mixed model analysis. Most of us use LME4. And just to state here that when you use LME4, the function you're using is LMER. And the way you write the function for LMER is you have the name LMER, open brackets, response variable, tilde, fixed effects part of the model, and then the random effects part of the model, okay? And of course, you need to specify the data frame that you're taking the data from. Because this is an LMER, we are assuming that it is a linear model and that the residuals should be normally distributed, right? If we were dealing with a non-normal error distribution, so Poisson, binomial, gamma, beta, then we would use a different function. We would use GL-MER, right? So the generalized linear mixed effects model. And if we have a GL-MER, then of course we also have an additional statement here specifying the family we're going to assume for residuals. So the output for the LMER looks like this. So I'm using a different example now. And the example is about radon in houses and basically looks at differences between top and lower floors. So the predictor is floor and the random effect is county. So this is a different location in the country. And we fit the model. And this is what the output gives us. It gives us scaled residuals. And then it gives us a part, which is the random effects. And under the random effects, it has county and residual. And it says county intercept, gives us a variance and a standard deviation. And what I want to point out to you is that this variance term here, which is the normal variance for the random effect, is this number, right? Oh, sorry, I've made a mistake. That should be a square. Right. And the residual variance is the one you're used to seeing. And in this case, the residual variance is this number here. All right. The next thing it gives you is how many observations we had in the data set. In this case, there were too many observations, and we had a huge number of groups. So when it says groups, it's telling me how many levels I have, how many different counties I have inside the random effect county. And then it gives me the fixed effects part of the model. And under that, it gives me estimate standard errors, t-value, and it doesn't give me the probabilities, okay? And the reason for this is that in LME, in mixed models, you can get quite complicated random effect structures, and it gets more and more difficult to estimate what are the true degrees of freedom of error. And remember that for t-distributions, you need to know the error degrees of freedom, otherwise you can't get the correct t-distribution, right? And so the guy who wrote this package removed the estimates for the t probabilities because he didn't trust the way they were being calculated. So LMER without anything else on will not give you t probabilities. So how do you decide whether something is significant or not? So the next question then is how to deal with inference. And just to repeat this, mixed effects models tolerate unbalanced and complex designs, but these often do not yield exact t-tests and f-tests because the degrees of freedom, and should I say rather the error degrees of freedom are hard to calculate. But we still can get to significance, and there are many methods that we can use. Likelihood ratio tests we've seen already. These models generate likelihoods, right? We still get true likelihoods for these models, and so we can still do likelihood comparisons between nested models. We can try and estimate the residual degrees of freedom, and if we can do that, then we can just use f-tests and t-tests again. And the last thing is we can use some kind of computational resampling to get at the coefficients. And a common one that's used is bootstrapping. So likelihood ratio tests, we saw this already in the GLM. Basically, this is where you compare nested models, a larger model, in this case, one that has the fixed effect floor, and a smaller model, in this case, it's the null model where floor has been removed. The random effect is retained, right? I'm not losing the random effect, it's still there. I'm just removing the fixed effect. And when I do that, I can again use the ANOVA statement to run a likelihood ratio test. And when I do that, it will give me this output, which says the models I'm running are radon with just a random effect for the counties, and model 1 with radon as a function of floor, a fixed effect, plus the random effect county. And these models only differ by one parameter, and that's basically floor has been removed from the null model. And so the difference between these two models is only one parameter. And again, the model will give me likelihoods, and it will give me deviances, and it will calculate a chi-square comparison based on the deviance differences between these two models. And in this case, the difference was 109, and the model concluded that there was a significant change in the variation explained, right? And so, well, in this case, in the deviance explained. And the conclusion being then that floor is significantly explaining variation in the response radon, and we should keep it in the model. We could then go back to the output and look at the coefficients to understand whether the coefficient is positive or negative based on that text. And so on that test, we would conclude it is significant and the effect is negative. So as we change floors, the amount of radon changes. The second test we can use is estimates of the residual degrees of freedom. And for this, there's at least two methods that can be used. One is Satterthwaite's method, and you can get this directly by installing the package LMER test. If you do this, then when you run LMER, it will automatically give you probabilities on the end. So if you just install the library LMER test and just run LMER again, now magically you will get probabilities. And these have been estimated. These are probabilities of significance based on estimated degrees of freedom for the residuals. And you can see them here. They are not whole numbers, right? How they're making this calculation, I don't know. I've never looked into the maths of that. Another way that you can look at residual degrees of freedom is the Kenwood-Rogers method. Again, it requires its own code. And the code that I've seen requires you to set up nested models. So you would install, oh gosh, I left out the package. I'm sorry, I will find the package and add it in and send you the lectures afterwards. But you run this command, komod.comp, and you need nested models for this analysis. And it's pretty slow in running. And it will also generate a residual degrees of freedom, which is not necessarily a whole number. And it will give you a test about whether there is a significant change between these two models based on whether you include floor or not. And the conclusion here is that there was a significant change. And what I read online is some experts prefer Kenwood-Rogers to the Satterthwaite method, but it wasn't clear to me why they preferred it. So I can't give you an answer on that. And then the final method is to do some kind of computational resampling, and bootstrapping is a common method to do this. This is basically where you generate new estimates based on subsets of the data. And if you run this very simple code, just conf specify the model that you had and specify the method you want to use. There are other ways you can do conf, but I always use bootstrapping. And this command, old names equals false, is just to make sure that the random effects are given names. If you don't use this command, it just says variance 1, variance 2. Right? So specifying this command will tell you exactly what the name of the random effect is. And then because it is a computational resampling method, you need to specify the number of simulated computations you make. And technically, if you're going to use this method, you should run it multiple times with different numbers of simulations to establish when the probability, the confidence intervals are stabilized, right? And so you run this code, and it will generate estimates for the parameters. And these will include both estimates for the variances and also for the coefficients in the model. So you can see here that it's giving you an estimate for the variance associated with county, and an estimate for the variance associated with the residual variance. And then the two fixed effects we have in the model, the intercept and floor coefficients. And what you do when you look at this result is you compare this interval against 0. If the interval is strictly less than 0, then we conclude that it is significantly different from 0. If it's strictly above 0, strictly positive, then we conclude it's different from 0. But if the range straddles 0, so if you have negative to positive values, then we conclude that actually it is possibly not different from 0. And on the basis of that, we can drop that predictor from the model. And this method, from my reading, is the best way to deal with the random effects. The random effects are not well treated with the other methods. So just to make that point, so take-home message about inference, there are actually numerous methods possible to decide whether things are significant or not. All of the methods I've shown you are okay for fixed effects, but the likelihood ratio and the mean probability tests are obviously not suitable for random effects. And for the random effects, maybe the best thing that I'm aware of to use is simply use the bootstrapping estimates of the coefficients. Okay. Then last points here. Oh no, still some stuff to do. Okay, so if I was doing model selection with a mixed effects model, my procedure would be I would write out the full model with all fixed and random effects. Then I would evaluate the random effects first and reduce the random effects as appropriate. And then I would evaluate the fixed effects and reduce the fixed effects as appropriate. And I would recalculate estimates after each removal, right? So I would do it in a stepwise way. I wouldn't remove everything at once. And once I've decided on what is actually important in the model at the end, then I would rerun the model so that I can get parameter estimates that are made with REML. Okay. Okay, right. Last things, model validation for mixed models, part 3. So for mixed models, we need to check normality of the residuals, but we also need to check normality of the random effects. And we should check homogeneity of the residuals. And the plot LM function that we use for ordinary linear models won't work here, so we can use a bit of constructed code to get at this. Firstly, for normality, it's very easy to plot the residuals using the QQ plot. And the QQ plot actually gives a nice result, this particular QQ plot function, because it gives you a confidence interval around the mean estimate of what values we would consider to be acceptable. So you can see that there's a QQ plot being done for the residuals and a QQ plot being done for the random effect intercepts. And for the random effect intercepts, it's clear that they're lying inside the confidence interval. There is some movement, but at least what I've been taught, as long as they lie inside the confidence interval, I would trust that result is reasonably robust for normality. For the residual errors, it's clear that there is some movement happening towards this end of the distribution. I'm not sure if that can be fixed, considering the size of the data set and how close it is to the line. I would assume that is not a big problem for the inferences being made. And then for homogeneity, again, remember for homogeneity, what we want, if possible, is that the residuals are approximately the same size, the mean residuals, regardless of the fitted value. If that's happening, then the model is running nicely through the data, right? That's the point, is that the homogeneity plot tells you whether the line is fitting through the data very well. And this can also be set up very straightforwardly with a bit of code. You just extract the residuals from the model you made, save them as resids, extract the fitted values from the same model, save them as fitted, and then you just want to plot the absolute square-rooted residuals. So we're making the bottom left plot against the fitted values. So if you had the ordinary LM plot, you know you get the 4 plots, basically. This is the bottom left plot. And then you can fit a line to show the average size of the residuals using this lowest function. and it's giving you the approximate average. And what you can see in this data, the homogeneity is very good, right? The line is very flat, and it's basically just below 1 across the whole range. So I would conclude that basically the model is fitting the data reasonably, and I can trust it and move on. Okay. And then the last bit, since some of you actually asked about this, I hope I understood the question correctly, but I think some of you were asking about how to construct more complex random effects. And I can talk about 3 of these. Maybe there are others that I don't know about, but these are the 3 I know about. And I call them simple, nested, and crossed. When I say simple, I'm basically just saying a single random effect, right? And that's a situation we've seen already. And when you write it pretty much just like this, right? So y is the response variable is some function of the fixed effects plus 1 given the random effects. But there's 2 other types where I have more than 1 random effect. And if I have more than 1 random effect, I need to think about the relationships between these random effects. And the one situation is when they're nested, and the one situation is where they are crossed. So we will talk very quickly about nested random effects. So this is a situation where we have nested random effects, and the property of the nested random effects is that the inner random effect only occurs. So let me say that again. Levels of the inner random effect only occur, that was a problem, in one level of the outer random effect. Okay, and so what I want you to look at is this experimental design. This was an experiment looking at the effects of diversity on land productivity. And the experiment was run in many countries in Europe. And basically the same experimental design, the same fixed effects design was applied in many locations. But in each location, well, in some locations, they had 2 blocks, which were repeats of the experimental design. In some locations, they only had 1 block. But what's important here is that these blocks are in different countries, right? And the values that you would get for growth in each of these countries is likely to be very different, right? And so in basically in Greece and Spain, oh no, it's Portugal, sorry, you expect very high growth rates, but in Sweden, you expect very low growth rates, right? So there is some difference between the countries. So that is a random effect we need to think about, right? That these locations are very different, and we probably need to use country as a random effect. And then the next thing is that in each of these locations, we have multiple blocks, and inside each of these blocks, we have all of the experimental treatments, right? And so we have a second random effect, which is the blocks, because we have all the treatments together here and all the treatments together here. And it's possible that there are differences between these blocks based on where they were put in the landscape. So the productivity could be different between the blocks. Clear? So we have a random effect for country and a random effect for blocks. But the critical thing here that makes them nested is that there are very big differences in the productivity of these sites. And so the productivity we would expect for these plots would in the south are probably much higher than the productivity we expect in the north. And so, oh, I see the thing is off. What we need to do is recognize that actually each of these blocks is uniquely located in its own country. So each block is strictly only related to its location, right? And so each block is nested inside its location, right? And we call this strict nesting. And if you have the situation, you can write the random effect in this way. You can say that the blocks, each block is nested inside a country, right? And so there's a random effect for blocks and there's a random effect for country. And the next part of this is that when you do this, you must make sure that every block has its own identifier, right? It must have a unique name. So you can't call the blocks in Greece 1 and 2 and the blocks in Switzerland 1 and 2. If you do that, then you don't have nesting, right? Because you're saying the block 1 occurs both in Greece and in Switzerland, right? So every block must be given a unique name. So it needs to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and I think maybe there's a 16 up there. Clear? Right. So that is nested designs. The second kind of design is something like this. This is called a cross-random effect design. The problem here is the person is interested in the growth rates of seedlings, and he wants to know whether the growth rates of the seedlings are differing based on the soil where the seedlings are growing. But the way he did his experiment is that he measured many different species. So he had different species of trees that he was measuring in each of these soil types. And he also had many experimental plots because he thought that maybe there were other environmental variation in the landscape, because maybe the alluvial soils are found across a valley, maybe there's something else going on there, and the mudstones maybe are found across the mountainside. So basically there's some other sources of variation. So he made many small plots inside each of these soil types. And those plots represent possible random information, right? Because the plots themselves may be different. And the other information here that's different is the species. Remember, I explained to you with the dogs that each of the dogs had its own characteristic blood levels, right? Similarly, each tree species could have its own characteristic growth rates, right? So each tree is a random effect level. So in this model, we need to recognize that we have a random effect for species and a random effect for the plots. And what's important is that if we look at each of these plots, so you've been given an example of 3 plots, the species are not all found in every plot, right? In fact, some species are not found in some plots. So the purple is only found in these 2 and it's not found here, right? And there are species that are found in multiple plots, right? So we don't have strict nesting here anymore. Basically, these random effects are doing different things in the landscape, right? And we need to take care of both of them, but they are not nested anymore. They are doing different things and they're not hierarchically directly related. So to account for this, we need to write the random effect model in a slightly different way. We don't specify nesting. We give each random effect its own separate term, okay? And that's how we would deal with a cross-random effects design. And then basically when you write your code in R, you can just use this structure inside the R code, and LMER will recognize that structure and identify that it's dealing with a cross-random effect as opposed to a nested random effect. Okay, and that's the end. So, Russell, back to you.
Thanks for the lecture. That was really comprehensive. I'm glad you went over a lot of the different types of these random effects models. I've struggled with a lot of them myself. One of the questions that comes up really often in the group, probably like once per week, is that people are often using the mixed effects models, but they don't know how to report the results in terms of effect size for each of them. So say you run a mixed effects model and your random effect is the site, but you want to report, for example, in a manuscript, like what the effect of each variable is per site. Is there any way to do that? I know I
don't understand why. To me, effect size, this I've been taught wrong. Effect size is the size of the coefficient, right? That's my understanding of effect size. Is that what they mean?
I think so. I mean, that's also my understanding, but people often bring up that there's a way to calculate like a pseudo R squared, similar to the R squared that you would.
Oh, that's not effect size. That's variation explained. right? So effect size is the size of the coefficient, right? That's what effect size is.
Okay.
It's a difference between treatments, right? So I didn't put that in. So there is a pseudo R squared, and that's the only one I've ever used. And I stupidly didn't put it here, but maybe I can just find it quickly. If you use, it's in the Moomin package, and it has recently been updated again. It was compiled by the Japanese guy from South Australia. Let me just see if I can find the code. Okay. Okay, so maybe just to point out that we actually run a much longer course than these 2 3/4-hour sessions to do this kind of work. Just don't know if it's there. Sorry, I gotta check it out.
It's all right. I can look it up and post it.
R squared GLMM. Sorry, just give me a second.
Take your time.
I'm just trying to think what R code is. I can't see my R code.
While he's doing this, anybody that wants to ask questions, please add them into the dialog box. Someone says, I think Nakagawa is the guy you're thinking of.
Yes, exactly. That's him. No, it's not this code. Sorry, I will find it and send it to you later. All right, sorry, I just didn't put it into the codes and I don't know where I've stored it. So AIC comparison was the one question. And the second question was R squared GLM function. Yeah, so basically Nakagawa and his colleagues made this function, and that, as far as I know, is the only one that I'm used to using, and I think that's the one that most people use. And of course, it is approximate, it's not exact, but it's fine, and it gives you enough information because it allows you to assess what information is due to the fixed effect and what information is due to the random effect, right? And that's often quite useful because then you can assess whether the fixed effect is actually explaining much information. And often it's not. Often most of the variation is explained by the random effect. And if it's significant.
Okay, so we have a question from, well, the first one is a comment from Stephanie who says, a few words about random slopes would be informative.
Random slopes. So unfortunately, I couldn't get my tablet to work. I was going to draw this because that would have made it easier for me to do. So let me go back to the lecture. Okay, so basically this might take me a little while to draw. Let's clean out some space here. Okay, so I'm just going to steal something so people can get an idea of what we're talking about here. Okay, so random slope model is the idea that basically, instead of just having a simple random intercept model, a simple random intercept model looks like this. It says that y is some function of fixed effects plus this. Oops. Okay, I hope that you all understand that notation now. So what this 1 here represents is, it's pretty much the same as you would think about if you wrote this model. That model is the null model. And the null model says that basically, null model is essentially just giving you a flat line, right? That's what a null model is. So it's a model where there is no relationship with the response variable, with the predictor variable. There's only an average value for the response variable. That's what the null model is, right? And if you think about that reasoning, then you can understand what's going on inside this term here, because this term is essentially saying, give me intercepts for each of my random effect levels, right? That's why it uses the 1. And so if you have a model written like this, it's saying, please only generate random intercepts. And in doing that, we are assuming that all of the slope relationships are identical, right? We're only assuming that there's some difference in the position where these intercepts, where these random variables cross the line. Is that clear? And in a random slope model, we're saying something slightly different. We're saying, so I'll have you draw it here, otherwise I'm going to run out of space. And you could write it just like this inside the LMER function. Now what I'm saying is that for the random effects, I can get differences in each random effect with respect to time. And that means that the slope lines are no longer parallel. They go in all sorts, whoops, let me get rid of that. They go in all sorts of crazy directions, right? Stop moving. Right? Anyway, I hope you get the idea. Basically, a random slope model says that we can have random slopes for each of our random effect levels. That's what it means, okay? And I'm just trying to think of a situation where you might obviously get this happening. Trees doing different things. Yeah, so maybe you were interested in tree growth rates. You were looking at tree rings. Tree DBH, and maybe if you looked at different species, all right, so I'm just going to kill this now. Then maybe basically each of these different lines represents a different species, right? And you're just interested in what is the relationship of tree DBH with time in the landscape, but you need to take care of species differences. Now, I hope you can appreciate that if you have lots of data, that the DBH increase is not a fixed thing. It could change depending on the species. Some species are fast growing and some species are slow growing. So it's quite possible that you could have different slope relationships between DBH and time for each species. But you're only interested in estimating the overall slope relationship in the landscape. Of course, they wouldn't be negative like that. They should all be positive, right? But they could be different. And so you would initially maybe plot the data and plot by different species to see whether you're getting different slope relationships for each species. I would do some pre-analysis just with the graphics to see what's going on. And if you conclude that, yeah, maybe there could be different slope relationships for each random effect, then you would write the model in this format, right? And this would then allow the model to have random slopes. Now, the first thing you should then check is the random slope really necessary or not? And you could use the computational bootstrapping on that model, as we did before, and you would now have an additional line of data here, which would be SD intercept dash county. That would be for the random intercepts. And you would have another line here, SD slopes, or actually it would give you, in this case, SD floor given county. So it would give you the slope relationships as a separate variance component. So basically you would get two variance components, one for the random intercepts and one for the random slopes. And then using computational bootstrapping, you could then test whether the random slopes is actually accounting for significant variation in the data or not. And if it isn't, you would drop it. And I guess I didn't point that out, but basically, when you're dealing with variances, they cannot be negative, right? Variances are strictly positive. So our conclusion about whether a variance is significant or not is whether it touches 0 on the lower boundary or not, right? So if it touches 0 on the lower boundary, then we would conclude that actually, no, it does not explain significant variation in the data. But if it is strictly positive, then we would conclude that yes, it does explain significant variation in the data.
Okay, so we have a couple more questions if you have some time. The first is, I mostly work on insects in different forests and also different forest types in which there are several transects. So can I say the insect data is affected by the nested structure, or there is also some crossed random effects? If both exist in the same data, how can I tell or how can I handle it?
Basically, the transects are being done in different forest types.
Yeah, the transects in different forest types of different forests.
Yeah, I guess I would set that up as a different forest types of. So basically, each transect is then linked to a forest type, right? And it's linked to a location in that forest type. That to me is a nested design. It's spatially separated, right? That transect cannot occur in multiple forest types. It can only occur in multiple locations. It's only in the one location, right? I don't know if that idea is clear to you. I tried to make that clear early. Basically, it's spatially located information, and it cannot be in more than one location, each transect, right? So it's a nested design. The short answer.
Yep.
Okay.
The next one is, what is your recommendation about inference on fixed effects, bootstrapping or LRT?
I think most people seem to think LRT is the most robust. So, sorry, not LRT, bootstrapping. I use bootstrapping. So, I mean, I always prefer these methods where we search the data space better, right? Under the assumption that it's possible that the data you collected is a particular subset that gives you particular relationships, right? So bootstrapping allows you to try different combinations of that data to make sure that the effect you found is stable.
Okay, we have one more question from someone who says they apologize. They came in a little bit late, so they're not sure if you said this or not. But their question is, how would I interpret the magnitude of the effect of random variables, and what if it is greater than the fixed effect?
So I think this is the same question that's being asked about the variance,
By me.
the variation explained, right? Yeah, like the pseudo R squared. I mean, that's kind of up to you, right? Because you need to make the decision then. the statistic may show that both things are significant, but it's very common that the random effect explains more of the variation than the fixed effect, right? And that doesn't mean that what you found is junk. It's just a property of the data you have, and you as a scientist need to make the valuation afterwards about whether you think this is a problem or not. This is not a statistical problem, it's more a thought problem about what your data actually means.
So overall, yeah, it goes back to expert opinion and as a researcher, yes, what you know, right?
Yes, but it's, so I mean, like in the radon data, I mean, I think the amount of variation explained by the difference between the treatments is less than 5%, and the amount of variation explained by counties is 30% or something, right? So obviously there's huge differences between counties. Nevertheless, as radon is a gas that people are scared of, the significant difference between the upper and lower floors means that you should avoid lower floors, right? So it may not account for much variation, but it is a significant effect after you correct for the county effect.
All right, that looks like we have all the questions. You've answered all the questions. We have a little bit of a statistics debate going in on the YouTube, so I'm kind of monitoring that right now.
So there are people who are better statisticians than me who have better answers. And
no, they're going off of the original, the initial question that I answered about the pseudo R squared and like doing a little back and forth about what the effect size could mean. And I don't know, it's interesting. You should check out the link at some point. But I think that we're going to finish the talk there and then go over to our next speaker. Thank you so much for the lectures on both of these. Like, it's definitely helped me. I'm sure it's helped everybody else understand GLMs and mixed models a little bit more.
Well, I'm sorry for the things that I couldn't answer, but I mean, I'm an ecologist, not a statistician, so there's kind of deep mathematical questions there that are just beyond my knowledge at this stage. So,
and I think that really opens people up to more questions and what they should be researching and understanding as ecologists too, to further their understandings of the two types of models.
No, I mean, they're good questions, and I will try and follow up on those too, and I'll try and get that R squared GLM function to you when I remember where it is, which won't take me long. Okay.
All right. Thank you very much.
So, bye.
Sorry, I closed all of my documents. Michael, are you there? I can let you do your introductions. There you are.
You see me now?
Yep.
Great. There we are. Okay. Hi to everybody. This is a very innovative event. And I think we have to thank Russell. He's doing such a great job putting it all together. Now, I know my talk, the title and the contents are quite controversial. So there's going to be a lot of debate after it. It's something I've always wanted to say. And thanks to Russell, I spent more than a week working on this to prepare the talk. Now, I must say right at the start, I don't mind anybody using the Bray-Curtis dissimilarity. I'm only exposing the reasons why I personally do not want to use it. And I think I've got pretty good reasons. So let me start off in all my presentations, my talks, and my videos I make online in the Karma Network YouTube channel, I start with a limerick. So for this very special event, I prepared 3 limericks. Here's the limerick summary of my talk. 2 botanists called Curtis and Bray came up with an idea one day. To distinguish samples A and B, let's invent a dissimilarity which their essential difference will convey. Their idea was simple, as you'll see. So Bray-Curtis gained popularity, but count data being notoriously skewed, transformations they had to do to balance large counts with rarity. But for me, on closer inspection, their index has gained disaffection. When large count ranges are found, size and shape differences do confound, which, after detection, lead to Bray-Curtis rejection. Well, the key words in red there you'll see are dissimilarity, skew, transformations, size and shape, confound. These will all be dealt with in turn. And I think this is a pretty good summary of my talk, actually. First, what's all this about, basically? Why dissimilarity, distance, multivariate, size and shape, and so on? In certain areas of ecological research, we could have count data, for example, species abundances in a set of samples from transects, quadrats, or volumes. The data could also be biomasses, and then what about all the environmental parameters? We'll stick to species abundances for this talk, like the stations by species data set shown here. If we just had one species that is univariate data, then comparing samples is very simple. To compare multi-species samples, we need to be able to measure difference between the samples. We need to know which samples or sample groups are similar and which are different. So we need some measure of multivariate proximity between them. And once we have this measure, then a low-dimensional ordination, for example, which is like a map of the samples, can be achieved, or alternatively, a cluster analysis. So this proximity measure is essentially the multivariate generalization of a simple difference in the univariate case. We have the multivariate equivalent is the proximity measure. Now I'm going to talk mostly about the popular Bray-Curtis measure of dissimilarity. And I'm going to contrast it with other measures, for example, the chi-square distance. My question will be, what is the actual nature of the difference that Bray-Curtis is measuring between two multivariate samples? I've read so many times in the literature that Bray-Curtis is a measure of compositional difference. Well, for the last 20 years, I've been working in the field that's called compositional data analysis. And it's become clear to me that the word compositional, used by many authors in the Bray-Curtis context, is not what I understand by this term. Notice too that this choice of proximity measure is absolutely fundamental to everything that is done afterwards. It's the first step and it has repercussions all along the way. Unfortunately, in software like the R function VegDist, which is in the package Vegan, and the commercial package Primer, the Bray-Curtis dissimilarity is the default method. So I suspect many users simply accept this default as if it's what they need. If you look at the Primer manual, you see it gives Bray-Curtis as the first option. And the manual also says, relevant defaults will be suggested given the data type. Measure Bray-Curtis for biota. There we are. If you've got biological data, counts, biomasses, use the Bray-Curtis. That's the relevant default. Well, I wish there was no default specified in either of these. So users would have to think a bit before they make their choice. So let's get started with some explanation of what the Bray-Curtis dissimilarity is. It's clearly been enhanced by the type of advertising it gets by the software packages. So it has become to be one of the most popular measures of between sample difference used by ecologists. All the data have to be on the same scale. For example, there are counts in this data matrix I show you here. It's a data matrix of 30 sites by 5 species. So to compute the Bray-Curtis between sites 1 and 2, for example, you sum the rows, the 2 rows, you get total counts of 27 and 54. And then you add up the absolute differences between them. So it's a difference of 26 on species A, 2 on species B, 4 on species C, and so on. And that gives you a sum of 37 differences between the sites. Then the Bray-Curtis dissimilarity is simply the 37 divided by the total counts in the two samples. That's 27 plus 54. So you get a value of that ratio of 0.4568. And this is often expressed as a percentage, 45.7%. Bray-Curtis will be 0 when the two sets of counts are exactly the same. Remember, they have to be identical. And it's equal to a maximum of 1 or 100% when there's no overlap between the counts. That is, wherever there's a positive count in one sample, the corresponding value in the other sample is 0. While ecologists might not be sure exactly what Bray-Curtis is measuring, they are very happy with a measure lying between 0 and 1. And that feature contributes to its acceptance. So we compute this measure for all pairs of sites, and that leads to a triangular matrix of dissimilarities. See, the ring value is the one we just calculated. Notice in the formula for Bray-Curtis that the sum of absolute differences in the numerator is nothing else but the Manhattan or city block or L1 distance. Often Bray-Curtis is applied to a matrix that has constant row sums, in which case it is misleading and a distractor to call it the Bray-Curtis, when it is really the Manhattan divided by a constant. One obvious and recognized problem with Bray-Curtis is that there will be large between species differences for more frequent species, which will then dominate the measure. So a transformation is required to compensate, often a square root or fourth root or log 1 plus x, which is a rather ad hoc decision with no clear way of deciding which should be used. For example, why is it always a square or a fourth root and never a cube root, for example? Although the Bray-Curtis definition has an understandable scale for the untransformed data, which adds to its popularity, getting a handle on it is not at all clear for transformed data. For example, what does a Bray-Curtis value of 50% mean for fourth root transformed counts? I don't know. The division by the sum of the counts, or usually by the sum of root transformed counts, is an attempt to make the measure compositional. But as I will explain, this doesn't always work out like we might expect. Now, for comparison purposes, as a contrast to Bray-Curtis, I have chosen to explain what the chi-square distance is, which is also popular amongst researchers who use correspondence analysis, either the unrestricted form or the constrained form called canonical correspondence analysis, or CCA. In a preliminary step, the values in each row are divided by their row sums, where these rows are what I call the sizes of the rows, thus eliminating the size differences between the samples and transforming counts in this example into relative counts, called profiles. In addition, the column totals of that matrix are also relativized in the same way, giving what's called the average profile. Now, in the language of compositional data analysis, the profiles and the average profile are all compositions, summing to the constant 1. I say that these compositions describe the shape of the counts, their highs and their lows, and are not directly affected by their sizes. But these compositional profiles may be related to the sizes, of course. To make an analogy, big fish do not always have the same shape as small fish of the same species. Now, to compute chi-square distances, let's look again at the first two sites. To compute the square of the chi-square distance, that's the chi-square distance squared, you take the sum of the squared differences between the profile elements, where each square difference is divided by the corresponding element of the average profile. These terms are summed, in this case between sites 1 and 2, you get a value of 1.297, and then the square root is taken to get the distance of 1.139, which is the first value in this triangular matrix of chi-square distances between sites. Now notice that the division of each squared difference in that sum, the division of each squared difference by the average or expected value, is the chi-square distances way of compensating for the frequent versus rare relative counts. And there are solid theoretical reasons for this type of standardization. Also, the distance is very similar to Euclidean distance, just with the added insertion of these compensating weights, which is why I call the chi-square a special case of a weighted Euclidean distance. Now, to contrast these two approaches to measuring multivariate proximity, I'm going to take a very simple example of two rows of counts. The first row has counts 1, 2, 3, 4, and 5, totaling 15, and the second row has exactly double the counts 2, 4, 6, 8, and 10, totaling 30. These are two samples with exactly the same shapes, but different sizes. Euclidean distance is the square root of the sum of square differences equal to the square root of 55. The Bray-Curtis is the sum of the absolute differences, as we've seen, divided by the total count in the two samples, and that's equal to 15 over 45, that's a third, 33 and a third percent. The chi-square distance first divides out the row sums, and so it is 0. If the data are log transformed, Bray-Curtis is 0.266, and if the data are fourth root transformed, Bray-Curtis is 0.086. Of course, if one divides out the row sums, then we get identical rows of relative counts, and any measure of dissimilarity or distance is 0. Two important conclusions from this very simple example. Firstly, when the shape of two samples is identical, Bray-Curtis still measures the difference between them, totally depending on their sizes. Secondly, a stronger and stronger root transformation is just bringing all positive numbers closer to 1. And if there are 0 counts, the strong root transformation is bringing the data set closer to a presence-absence 1. Now, I'm really going to rub all of this in steps, and so here are some first take-home messages. Bray-Curtis is affected by the difference in the sizes, that is, overall abundances of the samples being compared. It follows that Bray-Curtis only makes sense for samples taken from equal transects or equal areas or equal volumes. But even in such physically equal size samples, there are inevitably differences in overall abundances. And these differences also count to a greater or less extent in this dissimilarity. I'll soon show you a data set where the total counts of the samples ranges from a minimum of 54 to a maximum of 13,065. Okay, now let's look at a variation of this simple example. All we're going to do is we're going to interchange the two pairs of counts, swapping the 2 with the 4 and the 4 with the 8. We now have two samples with different shapes and practically identical sizes. The row sums being 22 and 23, practically the same sizes, but the shapes have changed. Since the absolute differences remain identical, and also the total counts in the two samples, both the Euclidean distance as well as the Bray-Curtis distance do not change. So now the Bray-Curtis value of 1/3, which previously measured pure size difference before, now measures pure shape difference. Anticipating my conclusion of this talk, the main reason why I don't use Bray-Curtis is that you're not sure how much a particular value is affected by the size part of the sample difference and the shape difference. On the other hand, computed on the relative abundances, which is pure shape, we're now getting some positive values measuring the shape difference in different ways. And remember that the Bray-Curtis reduces to the Manhattan distance. Well, I could actually stop this talk right now. The point is already being made in these two extreme cases. But let's add some more take-home summaries and then dig a little deeper into this issue. Bray-Curtis can in extreme cases be measuring just a difference in total abundances or measuring just compositional difference in the relative abundances. In practice, it will be a combination of both. And if it is used on data with constant sums, there's no need to call it the Bray-Curtis dissimilarity. It is then a well-known distance function. And then what about this dissimilarity versus distance story? Bray-Curtis is not a distance, since it does not obey the triangle inequality. Hence, it is called a dissimilarity or a semi-metric. And a part of its variance cannot be visualized in our Euclidean world with its Cartesian coordinates. Most likely for this reason, it is usually subjected to non-metric multidimensional scaling, not a metric scaling method. Paradoxically, the metric properties of the non-metric scaling coordinates are then used to correlate with species and environmental data afterwards. On the other hand, a Euclidean type distance such as the chi-square distance has very favorable and familiar properties, such as Pythagoras' sum of squares theorem and the decomposition of variance. And decomposition of variance is pure Pythagoras. Now, I've talked up to now about size and shape using these extreme examples, but in practice, is it possible to decompose any proximity matrix that measures between sample differences into parts that are size and shape? Well, this won't be possible to separate them exactly, since there will almost always be a relationship between the composition of a sample and its overall abundance. It is possible, however, to quantify the following variance components. And yeah, this is thanks to an idea by Burkhardt, Legendre, and Drapeau, who separated spatial and non-spatial variance components in this way. So we can separate the following variance components. Firstly, strictly size, which is uncorrelated with shape. And then strictly shape, that's uncorrelated with size. And finally, size and shape confounded. Then the function Adonis in the vegan package is just what we need to compute these parts. So here's some R code to do it. Okay, I'm using a data set here of 41 fish species abundances in 158 samples from the Barents Sea in North Norway, based on 15-minute trawls. First, the univariate size variable is just the row sums of the data matrix fish, and the multivariate shape variables are the relative abundances dividing each row by the respective row sum. The Bray-Curtis dissimilarity matrix is computed using function vegdist in the R package vegan, which has Bray-Curtis as the default, which I said is unfortunate because it reinforces its choice by the user. Notice that the range of sizes is very wide, going from 54 to 13,065. There are 4 components of the dissimilarity that are computed. A, size not shape, B, size and shape, C, shape not size, and finally D, a residual part with A, B, C, and D summing to 100%. I won't go through all the code except to point out the results for this example. 3.8% pure size, 4.7% size and shape confounded, and 71.3% pure shape, and there's a large residual of 20%. These 4 components can be shown as a compositional bar plot. Okay, and in a similar way, I can do all these calculations for the chi-square distance. Notice on the right for the chi-square that the pure size and residual components are completely eliminated. But there is a small part of 2.5% that confounds size and shape called, you'll see size confounded with shape 2.5%. As I say here, that 2.5% size and shape component for the chi-square gives a realistic idea how much shape is related to size. Not very much in this data set. But the part due to size increases to 8.5% in the Bray-Curtis, and that pure shape component reduces to 71%, with a large residual measuring something else that we are not aware of. It would be very interesting to know what that residual part is, but it is partially due to the dissimilarity nature of the measure, which is not Euclidean embeddable and thus incompatible with the notion of variance. My conclusion from this is that with the chi-square, I know very well what I've got, what it's measuring. In this case, almost pure composition, which is by design. Whereas in the Bray-Curtis, what it's actually measuring is much less clear. It's a bit of what we say in English, we call it a hodgepodge. This is an English expression which means a confused mixture. So take time for some more take-home remarks. We can measure the components of what I call pure size and pure shape, as well as the components affected by both size and shape. In empirical data, the component of size, including the size and shape component, that confounded part, can range from about 5% to about 30% in my experience. Multivariate analysis is used to relate the sample differences to differences in environmental parameters or to compare groups. So it will be difficult to know how much these results have been influenced by the totals in each sample as opposed to the sample compositions if we're using the Bray-Curtis. Well, I'm going to, after those simple examples, let me take a real experimental situation as a final example. Okay. And this experiment was ecotoxicology experiment. It consisted of 30 sampling units distributed randomly across across three treatments. There were 10 sampling units for the control. I label it as C, 10 for treatment 1, labeled as T1, and 10 for treatment 2, labeled as E2. Each sampling unit was characterized by the abundance counts of 45 marine species. So we had a 30 by 45 matrix, and we've got this grouping variable into the treatment groups and the control. Using the Bray-Curtis dissimilarity on square root transform data, which is a very regular thing to do, a significant overall group effect is found. Very significant. And we get that p-value of less than 0.001 again using the Adonis function. It's a permutation test. And doing post hoc comparisons of the treatment groups T1 and T2 versus the control, again using Bray-Curtis, both are found to be statistically different from the control at the 5% level. P-values of 0.048 and p less than 0.001 respectively. Now, in this study, Bray-Curtis was specifically stated to be testing differences in community composition. And the conclusion was that significant differences in community composition were found between the control and each treatment. The $64,000 question is, what is meant by community composition? I'll come back to that. Now, looking closer at the data, however, it was found that there were statistically significant differences between the total abundances in the three groups. You see these box plots. You can see that the two treatment groups had lower counts than the control group. As we have seen, these differences are contained to a certain extent in the Bray-Curtis, the similarities between the groups. Well, to find these significant differences, I used the coin package in R, which is a univariate permutation test. It's one of the functions in that package. And that shows a highly significant difference in the mean total counts between the three groups, as well as between each treatment group and the control, with very small p-values, 0.029, 0.009. The question here is how much these differences in abundance levels have influenced the finding of the above significant differences in so-called community composition. Or maybe it's the only difference. Maybe this change in abundance levels is the only difference between the groups. This particular example is special because the number of variables is larger than the number of samples. So the shape variables explain all the variance. So there's no residual variance and there's no pure size component. Just by the way, if anybody's looking at my article on size and shape in the journal Methods of Ecology and Evolution, I missed this point in my article, and there's a very small computational error there, which luckily doesn't affect the conclusions of the paper at all. Anyway, to measure the effective size, we have to look at the percentage of size that is confounded with shape. The pure shape components of Bray-Curtis and chi-square are 84.7% and 93.4% respectively. Expected to be higher for chi-square since it is focused on shape. The size-related components are 15.3% and 6.6% respectively. And that difference of about 9 percentage points represents the additional size effect that's incorporated into Bray-Curtis. Should have revealed that before I said it. Okay. So just to repeat something I said before, that when you look at that 6.6% for the chi-square, that is a very good estimate of the variance, the connection, let's say, or the confounding variance between shape and size. Okay. So one could say 6.6% of the variance is a size effect that is related to shape. When you go to the Bray-Curtis, that is considerably increased because the actual size effect is being incorporated more into the measure. So what we did was, what was found was that if you do a permutation test following the canonical correspondence analysis, which is the one using the chi-square, that's the bar plot on the right, corresponds to that bar plot, that treatment T2 is significantly different from the control. Okay, T2 is still, in terms of the shape, still different from the control, whereas T1 is not. We only get a 0.39 p-value for testing T1 against the control. So now we have this situation. We've got two different results. We've got the situation that T1 is significantly different from the control using Bray-Curtis, but not using chi-square. And also that T1 has significantly less total abundance than the control. Well, my personal belief is that the difference in total abundances between treatment T1 and the control, let's see if it's not changing now. There we are. My personal belief is that the difference in total abundances between treatment T1 and the control, which is incorporated more directly into the Bray-Curtis measure, led to the conclusion that T1 was significantly different from the control. There's in effect no significant difference in what I call composition between the two groups. What I'm going to end with here is some summaries, some ordinations. And these are nice ways of summarizing the results. These are the multivariate ordinations of the Bray-Curtis dissimilarities and the chi-square distances. Okay. Added to these, I put the 99% bootstrap confidence ellipses for the group means. And this is an approach described in my paper in Polar Biology on the visualization of ecological data. Usually, non-overlap of these ellipses implies significant between-group differences, although it is better to compute the p-values to confirm. On the left for Bray-Curtis, the p-value between groups T1 and C is significant, and we can see that the ellipses do not overlap. On the right for the chi-square, the p-value is non-significant, and the ellipses are overlapping. Now recall the box plots of the total abundances, and that the univariate between-group test reported a significant difference in total abundance between T1 and C. This is a further illustration that the shape or compositional difference, what I call compositional difference between T1 and C, is not statistically significant. Whereas the fact that size is contributing more to the Bray-Curtis accentuates the difference between T1 and C and leads to them being significantly different. Soon I'm going to conclude by recommending that size and shape be investigated separately. But maybe I am misunderstanding what ecologists mean by community composition. Would they really prefer to have size and shape confounded in one measure of sample difference? And if so, does that mean that it's okay to use the Bray-Curtis? Well, in this case, however, I see no justification for you choosing Bray-Curtis either, because there are other much better behaved true distances that also confound size and shape, and I would prefer using them. So I'm going to give you two alternatives. The first and the most obvious one is simply to use Euclidean distances on log transform data, of course with no standardization after log transforming. And if you've got count data with zeros, one has to be added before logging, which is a standard way of fixing up that transformation. The corresponding ordination using redundancy analysis is shown here. The T1 and C ellipses do not overlap, and a permutation test shows them to be significantly different, just like for the Bray-Curtis. Another option, little used up to now, uses what I call the chi-square distance on raw data. Also incorporates size and shape. Remember, the usual chi-square distance only analyzes shape, but when you do this type of chi-square distance, it imports the size effect back into the distance measure. This distance operates just like the regular chi-square distance, but does not relativize the data initially by dividing by the row sums. So that is raw counts, not profiles, but or relative counts. Raw counts standardized in the chi-square way are analyzed, and so the size is not removed. Again, T1 and C are shown to have non-overlapping ellipses, and the low p-value confirms they are statistically significant. Now, to my way of thinking, one of these is much better than using Bray-Curtis, if you think of overall abundances as an integral part of what you understand by community composition. And they are Euclidean type distances. And I might add that if the real experimental difference between a treatment and a control was only that the treatment reduced the overall abundances of my species and not the relative abundances, I would certainly like to know that. Well, that's the time to finish off now and summarize the previous take-home messages and some additional ones. Some general remarks. Beware of the size and shape components in the measurement of multivariate proximity. I would recommend to separately study and test the effects of size, univariate, and shape, multivariate, in the analysis of data such as these, such as abundances, biomasses, etc. Firstly, make a univariate permutation test of size effects, for example, of the total abundances or the species richnesses, and then make a multivariate permutation test of the shape effects, for example, using chi-square distance inherent in CA or CCA, or other distances that measure only shape, such as Hellinger or log ratio. And now some specific conclusions about Bray-Curtis. Bray-Curtis dissimilarity, which is not a well-defined distance, measures both size and shape differences, as I've shown, unless sizes are constant across the samples. Conclusions using Bray-Curtis can thus be affected by differences in sample totals. If you really want to analyze size and shape jointly, there are alternative Euclidean type distances, as I've just mentioned. As I said before, I'm not worried about you using it. I'm explaining why I don't use it. It's a free world, but you have to be very aware and be wary of Bray-Curtis. I've decided that there are other options with more favorable properties and less ad hoc decisions to be made along the way. And this is why I decided not to use it. Okay, that's it. I just give some references here, as well as to my books. Much of what I presented and more is in my article in Methods of Ecology and Evolution in 2017. There's also the reference to the second reference there's to the correspondence analysis of raw data in ecology, which explains that alternative chi-square distance that incorporates size into it. Also want to alert you to the website multivariatestatistics.org, which contains some of my open access books, especially the one that's the basis of our course that we give in Norway, the multivariate analysis of ecological data. Also repeat the limericks, given at the start, since they essentially summarize quite well the message of this talk. I'll give you my email address, and several web links. And I've highlighted that last one, Karma Network on YouTube, is where I put all my presentations. There's quite a few there. And this talk that I've just given is already pre-recorded, and it's going public here in about 15 minutes as soon as I can connect to YouTube and open it up to public viewing. I just want to conclude. A recurring theme in all of this that I've tried to expose here is to try to understand what ecologists mean by community composition. In one of her papers, Marty Anderson says, speaking about the Bray-Curtis dissimilarity, and I quote, "An important ecological issue is to understand how much of the dissimilarity is driven by compositional difference and how much is driven by differences in relative abundance, which is difficult to ascertain for the Bray-Curtis and related measures." Unquote. So already with that statement, I'm confused, since I understand compositional difference to mean difference in relative abundances, taking my cue from compositional data analysis. So what I've tried to show is how much Bray-Curtis and other measures are driven by what I understand by compositional differences, that is shape differences and differences in overall abundances or sizes. So I hope we can clarify the terminology and objectives in the future. Thank you very much, and I invite you to keep in touch. Thanks to Russell for everything. Thank you.
Well, thank you for your talk. That was definitely insightful. You're multi-talented, a statistician and a musician. Is there anything you can't do? I think that's really, it brings up a good point that sometimes we use our functions as ecologists and not strong statisticians without actually looking into what's under the hood and actually trying to understand what it's doing for us. Because I have definitely Bray-Curtis before, after reading the documentation of the veg dysfunction, and it's just like, well, we use Bray-Curtis as the default with really no other explanation other than that's just what we do. So I think that's really insightful. So we do have a couple questions. The first one is, somebody said, interesting subject. Could you be persuaded for the use of model-based ordination methods that don't require the use of distance measure at all?
Model-based, what type of methods? Model-based methods?
That don't use distance measure at all. I'm honestly not sure how you would do that with something like multivariate.
Yeah, I don't know. I mean, you have to know you have to be able to measure differences between your samples to do anything. So if you don't have a measure of difference, I don't see how you can do anything. And I'm not sure what models what the person means, what type of models. I mean, all of these things are models in a way, but they're sort of like distance-based models. And they're trying to explain the distances using groupings like clusters or multidimensional scaling, making these maps to understand the group differences or how they're related to environmental variables. If you know the distances, or if you have some quantitative measure between your samples, then you can start relating that to the differences on the environmental variables, just like we do for single univariate responses. We have a single univariate response, we're relating it to an environmental variable. So the analogy is just you go to the distance function, the difference function between the samples, and you can do exactly the same thing.
Okay, we have, they followed up with, have a look at the GLLVMR package too. I'm not personally familiar with that. I assume it does something with multivariate scaling data or something.
Yeah, I'm going to write it down and investigate it. GLLVM. Thank you.
Yeah, he says it stands for Generalized Linear Latent Variable Models, combination of GLL.
Okay, latent variables I know about. Yes, okay. Yeah, okay.
Okay, so we have another question from Duk, who says, I have a question related to NMDS. I want to show composition of species in different number of compartments, but the area of compartments is different. So is Bray-Curtis okay, or is it not?
Okay, well, I said during my talk that it's only Bray-Curtis is affected by the size, that the totals in every sample. So if you've got some of your samples that are just bigger than others, I mean, in area or volume or whatever, then of course it's inappropriate because it's going to show them even more the differences in the totals. So the Bray-Curtis only works for fixed physical size samples, whether it be along a line, whether it be a quadrat in botany, a volume in marine biology, or a transect, okay, or a trawl. I had the data from trawling. It was 15-minute trawls, exactly 15-minute trawls for every sample. So that's where Bray-Curtis is applicable, or is usually applied to. But I was pointing out that even in those fixed size samples, you get a difference in the totals in each sample, which is affecting the measure.
Okay, well, that definitely answers my follow-up question, which would have been, if you were going to use Bray-Curtis for a specific type of study, what would it be? So that's good to know that there is some application to it in very specific scenarios.
Yeah, for that, just to say that again, with that question, you could express your data per unit volume. I don't know what the actual data are, but per fixed physical size, and then you could use it. Subject to what I've explained, that you're going to have this totals and the shape confounded.
Is there any more questions? I'm looking at both the YouTube feed and here on Zoom. Well, somebody just left a comment in the chat box saying, wow, that's the first time I get things about the matrix distance very clearly explained.
Okay, thank you.
Anyone else? Okay, well, I don't see other questions. We can continue to discuss this on both the YouTube and in the Ecology in R Facebook page at your leisure. I'm sure there's people that are sleeping right now at some points in time around the world, so they're going to have to view this a little bit later. Thank you so much for your presentation, Michael. I appreciate all the work that you put into to presenting it today.
Thank you, Russell. Bye-bye, everybody.
Okay, so that's it for our 4th day of the Ecology in R web conference. We have another one coming up on, let me check the schedule here. That is 4 p.m. on March 5th. Oh, no, that's today, sorry. 3 p.m. on March 6th. That's Pacific Standard Time. So we'll be doing some talks on teaching ecology in R. So watch out for those talks, and I will see all of you guys later. Again, I will be posting this to the Ecology in R page, and our speakers are usually all on that page at some point in time or other. So if you do have some discussion points or some extra questions, you can ask them there, and I'm sure they'll answer you whenever they have the time. All right, bye everybody.